California.
Hello from Kharagpur, sir.
Okay, shall I just start?
Yes, sir. Yes, sure.
Okay, let me get the slides. Okay, is this good? Is it up yet?
So it's buffering. Yeah, it's up.
Ah, there it is.
Yeah.
Okay, good. Well, I'm Ashwin Vasavada. I'm currently the project scientist on the Curiosity rover mission. And we have just finished about 2.5 years on Mars. And so over the next hour or so, I'll tell you a little bit about what we've been discovering and then also some of the challenges that we've had in the last few years. And we'll take questions at the end. But if at any time the audio or video drops out, please let me know. So this is what the rover currently looks like. These are two self-portraits that we were able to take with the rover's own arm. So we have a 7-foot robotic arm that we can hold out in front of us and take pictures. And on the left was just about 3 or 4 months after landing, and on the right was a couple years after landing. So much more dust on top of the rover, but and the wheels are not as good shape, which we'll talk about. But these are just fantastic pictures that we can use to understand the health of the rover and also just document where we've been on Mars. So I'll start with just some basics. I think you're all enthusiastic about space exploration. I'm not sure how much everyone knows about Mars, so I'll just briefly cover some of the reasons why we explore Mars and why we sent Curiosity to explore Mars. So here, of course, you can see Earth and Mars is about half the diameter of Earth. Mars has polar caps like Earth, has seasons, and a day, just a half hour, 24.5-hour day. It has just a little bit of water vapor in the atmosphere, so you can see some clouds around it. Of course, one of the big things that Mars lacks today is an ocean. It may have had one in the distant past, and in fact, Mars is very exciting to study because we think 3 or 4 billion years ago, Mars may have had much more liquid water than it does today, and may have even had a thick atmosphere and the possibility of being somewhere that life could exist. Some of the reasons we think that are the pictures that are shown here. So these are some pictures going all the way back to the early days of space exploration. In the left are two things. So in the upper left are what we call outflow channels. These are flood channels that are bigger than any rivers on Earth today. Catastrophic floods that occurred on Mars maybe about 2 to 3 billion years ago. In the lower left are smaller channels. We call these the valley networks. So there are networks of rivers that flowed in between the craters on Mars. And this probably happened even earlier in Mars history, maybe 3.5 to 4 billion years ago. So there's quite a bit of evidence for flowing water on the surface of Mars in the distant past. And on the right is a beautiful example of a delta being where a river empties into a standing body of water. In this case, this is a picture of Eberswald Delta, where one of these valley networks flowed into a crater. That the crater presumably had a lake in it, so that when the river flowed into the crater, it formed a delta, just like, for example, at least in the United States, where the Mississippi River empties into the Gulf of Mexico, there's a beautiful delta just like this, made up of mud and sediment. And now, of course, the water is all gone and the sediment has turned into rock, but the shape of the delta is left behind. So, to simplify it very much, the reason we are so interested in studying Mars is partly because it resembles Earth, especially in its early history. The current picture shows what Mars looks like today, but in a distant past, Mars may have actually had an ocean. And in fact, there's evidence growing now that maybe the entire northern hemisphere of Mars was under several hundred meters of water in an ocean. And some of the places that we even explore with Curiosity may have been covered in lakes associated with that ocean. So it's pretty exciting to think what Mars may have been like 3 or 4 billion years ago and ask whether Mars ever was a habitable planet. And that really is the goal of what Curiosity is studying, is to figure out whether Mars could have ever supported life. So what makes a place habitable? When we talk about habitability on Earth, you can think of what it takes to support life on Earth, whether it's plant life or other life. One thing, of course, that we think is common to all forms of life is the use of liquid water. All forms of life, as we know it on Earth, require liquid water, and the nature of that water matters as well. For example, if the water is very acidic, then it's more difficult for life to survive. There are extreme forms of life who can make use of it, but the most friendly water for life would be something with a neutral pH, not too acidic, not too basic. The key chemical ingredients of life also matter. All of our cells and all the cells of all living creatures are made out of a few key chemical elements like carbon and oxygen and sulfur and hydrogen and nitrogen and phosphorus. These are sort of the what we call the building blocks of life. And we'd like to look for those also on Mars to see if the raw materials of life are present on Mars. And then finally, we all need energy to support our metabolism. On Earth, a lot of our energy comes from sunlight, whether plants using it directly or things like animals eating plants and then us eating animals. In general, we get a lot of our energy through the sun. But more extreme forms of life on Earth can use energy from different sources, like the energy between different chemicals inside of a rock or buried deep underground. And so we'll look for all sorts of energy pathways that could support life on Mars as well. So here's Curiosity. It's the rover about the size of a car, 6 wheels, 10 different scientific instruments, and all of the instruments were built to assess habitability on Mars. We're not looking for life exactly. We don't have experiments that look for living microbes, but we look at the ancient geology of Mars from this time period of 3 to 4 billion years ago. We explored the geology to read the record of the rocks to figure out if the environment when those rocks formed was a habitable environment. And so we have 10 different instruments. We have this mast, the head of the rover, which has science cameras called MastCam. It has this instrument that shoots a laser. It's shown here called ChemCam. This fires a laser up to about 7 meters away. And by focusing a laser on the rocks or soils around us, we can create little sparks. And these sparks we can then image with a spectrometer. And the detailed color spectrum of each spark tells us which chemicals are in the soil. So even by shooting a laser around the rover, we can already begin to see the chemicals that are in the rocks and soils. We also have the 7-foot robotic arm, and on the end of the arm, there's instruments that we use to sample the material. We have a drill and a scoop, both of which are used to acquire samples of the rocks and soils around us. And the real new capability of this rover compared to any other rover before it is the fact that we can deliver those samples of rock and soil to laboratories inside the rover. And we have 2 laboratories, one that's called SAM, you can see it labeled at the bottom, which is a mass spectrometer. And we also have a laboratory called ChemIn, which is an X-ray diffraction experiment that tells us exactly which minerals are present in the soil and rocks. And the minerals are very important because unlike the pure chemical elements, the carbon and the silicon and other things like that, knowing what minerals those elements have formed into is what tells us about the environment. The easy example is something like carbon, where it can be in a form like graphite or it can be in the form of a diamond. And the mineral form that carbon takes is dependent on the heat and the pressure and maybe the amount of water that was present when those minerals were forming. And so it's very important for us to understand which minerals are present. We have other experiments that are listed here. I won't go through them all, but we do have other experiments that measure the weather and measure the radiation on Mars to also look for the habitability of organisms on Mars. So you can have a very sophisticated rover and some very compelling scientific questions like habitability, but you still have to pick the right place on Mars to answer those questions. And so we spent several years looking at all the data from previous missions on Mars to find the best place to send the rover. And we started with about 60 different places on Mars, and over the course of a few years we went to 30, and then 10, then 7, then 4, and then finally we chose this site called Gale Crater. And Gale Crater is this 150 kilometer crater on Mars, and it has a very unique feature, which is a 3 mile or 5 kilometer high mountain in the middle of it, made of layered sedimentary rock. So that mountain in the middle of the crater didn't form with the crater. It's not the central peak of the crater. It's actually sediment that was brought into that crater and built up into a mountain over time. And in this slide, you can see a cutaway through the mountain showing that it's made up of this layered rock. And in the lower right, you can also see that oops, let me go back. In the lower right, you can see that the mineralogy changes. The bottom of the mountain, where the word clays is labeled, the bottom layers of the mountain are made of clay. We can tell this from orbit. And clay is a mineral that only forms when water interacts with rock over a long period of time. And then slightly higher on the mountain, the mineralogy changes to sulfates. Sulfates are more of a salt that is left behind when water evaporates and leaves behind minerals in the rock in the form of salts. And then above that, where it says the younger strata, that's just Mars dust, dry Mars dust. So even inside the mountain, as layers were forming one after another, we can tell even before we landed that the bottom of the mountain probably records a time period of Mars when there was more water forming the clays. The middle of the mountain probably formed when there was a time when the water may have been drying up and leaving sulfates. And the upper part of the mountain is likely composed of dry Mars dust, reflecting a time in Mars history when the water was gone. So this made this mountain a very unique place for us to send the rover to understand habitability, because we were able to go to multiple times in Mars history and ask the same question at each time in Mars history. You know, was this a time when the conditions were favorable for life? So in August of 2013, 2012, a few years ago now, we successfully landed on Mars. Of course, many of you hopefully were watching, and it was a very exciting time for all of us, especially after working on it for so many years. I started working on the rover in 2004. So it had already been 7 years until the launch and 8 years until the landing. And in a few minutes, we entered the atmosphere, slowed down from 6 kilometers per second all the way down to just walking speed as we gently lowered the rover down on the surface with rockets. And you can see there, we landed next to the mountain. So what you're looking at is the mountain in the middle of the crater. The lower units do look a little different from the upper units, and most of what you're seeing in the upper part of the mountain is that dusty layer, and all of the clays and sulfates are in the lower layer just above the dark band. And the dark band is actually dark sand dunes that are much younger than the mountain, that have then traveled into this crater and form a ring of sandy dunes around the mountain. But one thing that was very interesting, right after we landed, the rocket engines, you can see in the upper right how we landed with this mechanism that lowered the rover down and fired rockets as it hovered above the surface. And the rockets scoured away some of the gravel, some of the soil around, and you can see that on the right hand side of the bottom picture. where the upper layer of the red soil has been removed and some gray patches are there instead. When we looked at those gray patches in detail with our high-resolution camera, we found a type of rock that had never been seen before on Mars. And once the gravel and sand were removed, we saw this rock that's called conglomerate. And conglomerate is a type of rock where it's basically a bunch of small gravel and pebbles that are stuck together by some kind of mineral cement. So it's a rock that's composed of pieces of many other rocks. And we had never seen this kind of rock before, and it was quite exciting. And I'll tell you why in this picture. This is more of that same rock. You can see now it kind of looks like cement, like concrete on Earth. But really it's a rock composed of a bunch of small pebbles about the size of, about a centimeter across. And when we looked at the rock as it was falling apart, and those small rocks were coming out of it, we could see that they were rounded. And when you see pebbles that are rounded like this, there's very few natural ways of rounding hard rock like this. And one of the most common ways this happens on Earth is when those pebbles are transported along by flowing water in a stream, in a river. And the rocks might travel for miles and miles, being brought along by the currents and banging against each other and grinding against each other. And the edges are rounded off, and you get rounded pebbles. And this is what we were seeing. So even right after landing, we realized that we were driving through an ancient riverbed on Mars. And this is something that we thought we saw from orbit. I'll point out from this picture that even though the main target of the mission was the mountain itself, you can see where we've drawn the oval on the surface. That's our landing site area, and even from orbit we could tell that there was an ancient river system and a fan that spread across the crater floor. And so we were hoping that we would land somewhere near that fan and that ancient river. And after we found those pebbles, we realized we actually were driving across a place where water once flowed on the surface. So of course that was very exciting. This is a picture of where we spent about our first year. You can see on the left Bradbury Landing, named after Ray Bradbury. This is where we landed, and you can see the pictures. I mean, you can see the scars left behind where the rockets blew off the material from the surface. This is a picture taken by the Mars Reconnaissance Orbiter from about 200 miles above the planet, but you can still see the mark we left by landing, and you can still see the tracks of the rover as we drove across. And then we drove to the edge of that fan, the fan of material brought by the ancient river. We wanted to go see whether that fan of material really was evidence for flowing water, and maybe where the water ended up being more gathered into a lake. So we drove to this place that we called Yellowknife Bay, and you can see in this picture that when we got close to the area at the end of this ancient river, it looked very different. So instead of the gravel and sand surface that we were so used to seeing on Mars, now we were looking at this surface that was very much smooth bedrock and very fine-grained rock that was composed of very small particles, very much like you would find in what's called a mudstone on Earth. On Earth, you find this kind of rock very much where lakes present at one point, and the sediment in the lake, the very small particles in the lake settle out, form mud at the bottom of the lake, and then that mud dries and turns into rock over time. And so from a geologic point of view, we were already seeing here that there was an ancient lake in this area that was fed by that ancient river. And so of course we wanted to drive into this area and sample this mud at the bottom of the ancient lake to get our first idea of whether this may have been a habitable environment. As we were driving into the lake, we saw these layered sandstones. Now this isn't the mudstone, this is actually sand-sized particles, bigger particles. And in fact, the sand in these beds in these sandstones were so big, they were almost millimeter size, that they were too big to have been carried by air, by wind. So these are not sand dunes like wind would form, but these are actually ripples of sand that were also flowing along, being pushed along by water. Now this is a picture of the bottom of Yellowknife Bay at a site that we called John Klein, and this is where we did our first drilling. So here we are drilling into the mud at the bottom of this ancient lake, and you can see the mountain, Mount Sharp in the background, and we were getting our very first look at the rock of Mars. Here's our drill holes. Every time we drill, we start with a test hole. That's the test hole on the right. It's only about 1 centimeter deep, and the purpose of it is just to test the hardness of the rock and to make sure we set the parameters right when we do the full drill. Now the full drill is in the middle of the picture. It goes about 6.5 centimeters into the rock and gathers powder into the drill. And then that powder, we can first look at it. In the lower left, we can look at the powder we acquired inside of our scoop to make sure that we successfully acquire the powder, and then we deliver it to the instruments in the rover. And in the upper left, you can see the drill bit that we brought to Mars, and it is a rotary percussion drill, which means that the drill bit spins, and it also pounds up and down and chisels into the surface. So this is a summary of our laboratory results from this drill hole. These are the kind of data that we get from our 2 laboratory experiments. The upper right is from the X-ray diffraction experiment. Now this instrument shines an X-ray beam through the crystals in the rock. And just like when you shine light through a crystal and it goes into a rainbow pattern through diffraction, here we're shining an X-ray through the mineral structure of the rocks. The rocks are all made of crystals, and you get this very distinctive pattern of diffraction, and you can measure the angular distance between these arcs, and actually every mineral leaves a very unique fingerprint. So if you are an X-ray diffraction scientist, you can read these arcs and figure out which minerals are present. And the most exciting one for us is at the bottom where it's labeled phyllosilicate. Phyllosilicates are basically clay minerals. So here we are, we were able to find evidence that these rocks were made of 20% clays, meaning there was a lot of interaction of these rocks with water at one point when they were forming. And the fact that they were clay minerals means that the water was not only there, but it was also fresh water. It was moderate pH water, not too acidic. So, like we talked about earlier, we not only found water, but we found the kind of water that would have been most favorable for ancient or for Martian life, if it ever was there. Now, on the bottom plot shows you the results we get from our mass spectrometer. This is an interesting experiment where you take a sample of powder and you heat it up over time from the ambient temperature up to about 800 degrees centigrade. And as you heat it, the different minerals in the rock decompose and release gases. And you can measure those gases. So you can see at about 200 centigrade, we first saw a lot of water come off, and that's just the moisture that was absorbed into the rock. And then we saw CO2 and oxygen and sulfur dioxide, hydrogen sulfide. And then finally, at about 700 degrees, we saw another peak of water in the red dots. And that was actually the clay minerals. They're known to break down at about 700 degrees. So the fact that our mass spectrometer saw the clays breaking down, releasing water at 700 degrees was additional evidence that we had seen clay minerals on Mars. So putting all this together, starting with the geology, starting with the fact that we saw the rounded pebbles and the sand that flowed in water, and then the mudstones, and then seeing the clay minerals, we have a lot of different evidence now that this was a place where there was a lot of water in the past. You can see there that the mass spectrometer also found carbon and oxygen and hydrogen and sulfur. It's not shown here, but we also found phosphorus and nitrogen. So we found all of the key ingredients of life that life requires. And then finally, energy for metabolism was our third component of habitability. And we found, of course, there was sunlight there, in Mars past, but we also found what's shown in the bottom right there, the two forms of sulfur, sulfur dioxide and hydrogen sulfide. These, the fact that both an oxidized form and a reduced form of sulfur was present in the rocks is something that microbes on Earth can use to generate energy for their metabolism. They can live off these chemical gradients in the rock, deep underground. So we have at least two forms of energy that microbes could use. So this is really the biggest result of the mission to date, that this site on Mars would have been able to support life. We unfortunately still have no evidence of life having used this environment, but to know that Mars was capable of supporting life really was the goal that Curiosity was sent to figure out. And I've just explained all the words here, so I won't read through them again, but this is just all of our evidence for the habitable environment at Yellowknife Bay. So we spent about the first year of the mission exploring there, and then we went on and we drove across the plains to a site called the Kimberley, where we studied another rock formation that we'll talk about in a little bit. And then the goal was to get to the base of Mount Sharp and start climbing up the mountain. And so we targeted this site that's circled there with the blue oval as the path we would use to drive up. And if we drive up through that area, we would pass through the clays that we saw earlier and the sulfates, and eventually end where the mountain turns to the dry dust layer. And we think this will take several years to accomplish, but currently we're at we're just about where it says base of Mount Sharp. That's currently where the rover is. But on the way there, we ran into trouble. And this is where we had to figure out and make sure that we were still able to accomplish the rest of the mission. And the problem was with our wheels. Maybe you've already heard some of these stories, but this was a big problem. About the 400th sol of the mission, we did some routine monitoring of the wheels and realized that they were gathering dents and punctures and tears. They were actually tearing in the metal at a much faster rate than they had been designed for. So of course we anticipated these aluminum wheels would get some punctures and some tears over time, but we had tested them such that they would last for at least 20 kilometers, which is about the distance that we thought we would have to drive in the mission. But here, even after just a few kilometers, they were already getting pretty beat up. And we attacked this problem in two different ways. One was from the geology. So we asked some of our geologists on the team to look back at everything we had driven over and try to understand why the testing we did prior to launch was not reflecting how the wheels were actually behaving on Mars. And it turned out that we had tested a lot of what looks what's shown in the upper panel, where there's a lot of sand and gravel and some loose hard rocks. And when the rover drives over those loose rocks, they basically get pushed into the sand and the rover can drive over them. But what we were seeing instead on this mission that was not fully anticipated was embedded rocks, sharp rocks that were sharpened in some cases by the wind, by sand blowing and making very sharp points on the rock. But the rocks were embedded. They were like icebergs almost, where the rock may be buried below the surface and all you're seeing is the tip of it. So when the rover, even though it's a 1-ton rover, when it drives over these rocks, the rocks don't move. And a lot of the weight of the rover can end up being supported by a little tiny point on these rocks. And that's what can cause the damage into the wheels. And here is this is almost a funny picture of the worst case scenario you could ever imagine. We have this very sharp rock and you can see it's lifting the wheel off of the ground and probably causing some damage to the wheel. Fortunately, there's not many rocks like this, but we got this picture one of the days that we were studying this problem, and it really is an example of how bad it can get. We also studied it from an engineering perspective and trying to figure out if the way we were driving the rover or the way the rover was designed was causing the wheel damage to be worse than we would expect. And there was two aspects of this. You know, one is you can see the design of the suspension of the rover. There's the suspension arms, the two that are facing forward, so the rover drives to the left in this picture, and the two suspension arms are pointing slightly down. And this is actually causing the wheels, when they hit an obstacle, when the back wheels are still pushing the rover forward, this creates a force not only towards the front of the rover, but it also creates a force in the downward direction. So the fact that the rear wheels are still pushing the rover forward, when the front wheel hits an obstacle, it gets pushed into the ground a little bit harder than just the rover's weight, because those suspension arms are imparting a force that's a little bit downward because of the way they're angled. Meanwhile, the rear wheels are angled up. Their suspension's angled up, and so they're carried over obstacles pretty easily without causing much damage. And the example here that you can see with the bag that we all carry to the airport is a similar kind of thing. When you drag the bag behind you, it lifts up easily over obstacles. But if you were to push that bag in front of you and you hit the side of the curb, or you hit a rock, your force of pushing that bag in front of you actually will turn into a downward force, and you'll put more pressure on the obstacle. And that's what was happening. And this is very consistent with the damage that we were seeing, where the middle wheels, which have the most downward sloping suspension, have the most damage, and the rear wheels have the least damage. And so we've actually now redesigned some of the algorithms that control the motors on the wheels to allow the wheels to climb over obstacles without the rear wheels pushing them into them. So I just talked about all this, but these are the causes of the wheel damage. One is the metal fatigue from sharp embedded rocks, and the other is that the wheel can actually be pushed into the obstacle by the other wheels. So we tested a lot of this. We built this test rig in one of our test facilities at JPL, and basically this was built in order to make sure that our theories were correct. And you can see that when we designed this to act just like the wheels on Mars, again you can see that the middle wheel has the most damage, the front wheel has some damage, and the rear wheel has very little damage at all. And this was also built to test the life of the wheels, so we could see at the current rate of damage that we're getting now, how long will the wheels last. So what you can see here on this picture is wheels that have driven a lot more than the wheels have on Mars, so they're much more damaged. And yet, even in this state of being very heavily damaged, the wheels still provide full structural support to the rover. So the wheels have not failed here yet, but eventually they do fail, and especially the middle wheels start falling apart. But we think after all this testing that we now are smarter about how we drive, and we still will be able to finish out the rest of the mission just with a little bit more careful driving. So some of that careful driving is shown here, where now we drive in the bottom of these valleys. Where the green is are actually sand-filled valleys. You can see there. And so now, instead of driving on the harder rock on the higher plateaus, we try to find valleys to drive down into, because the sandy floors of those valleys are safer for the wheels. And this just shows you the effort we take to find paths. So when we're driving into new terrain, we have to spend several weeks mapping out these paths and looking at the orbital imagery to make sure that they're safe and that there are obstacles that we can avoid. One of our favorite paths required driving across this dune. So unfortunately, there was a beautiful path we wanted to take, but it had a very narrow valley we had to drive across, and this 1 meter high sand dune was blocking it. And we drove carefully to the top of the dune before we fully committed the rover to driving over it. We were worried we would slip in the sand and maybe get stuck. And we could see just on the other side of this dune, there was a beautiful, safe path. There's a few boulders, but we could drive around those. And then after that, it's just a very nice, smooth path for the rover. So we studied the dune pretty carefully, and then finally one day we decided we wanted to go for it. And we drove over it, and actually the rover performed very well and drove over the dune without slipping very much at all. And then we had a very nice several kilometers of safe driving. So here are the wheels, what they look like these days. They aren't pretty. They have some pretty big holes in them, but so far structurally they work the same as they were when they were new. So no problems yet. We just have to be careful about not increasing the damage too much. So onward to Mount Sharp. So we crossed Dingo Gap. Dingo Gap was the place with the dune in front of it, and we went on to the site called the Kimberley. The Kimberley here, this is an orbital picture, again showing the rover, where the word Curiosity is, and then you can see the rover tracks. The Kimberley is an area right near where the rover is parked, where several types of rock all came together. We like, as geologists, we like seeing where all these different rock types are next to each other, because then we can get a clear idea of the age relationship. When we see them apart, we don't know which came first, but if we see them like what's shown here, we can tell that the rock that the rover is sitting on is the oldest, followed by the smoother rock above it, and then followed by the rock that forms the little mounds, the buttes, that must be the youngest. Here's what that looked like when we were close up. We saw that, again, these beautiful tilted sandstone beds, again made of sand that was too big to be carried by the wind, but instead was carried along by water in an ancient river, and leaving behind these very distinctive tilted sandstone beds that tend to form when water is flowing from a river into an ancient lake. And so these are actually deltas. We think these are miniature river deltas, where there was a lake on the left side of the picture and a stream on the right side of the picture. And what you're seeing here in these tilted sandstones is just where the river was entering a lake and dropping its load of sand and silt into that lake. And this is just another picture of the same rocks at the Kimberley. And this is where we drilled at the Kimberley, our second drill hole. We again found clays here, not as much clay as before. So not quite as habitable an environment, but still a very good environment to support life. This is the drill hole at the Kimberley, showing how our laser can shoot little spots even inside this drill hole. So this drill hole is very small. It's only about 1 centimeter across, and our mast where the laser is about 2 meters off the ground. So from a height of 2 meters, we can shoot this little pattern of laser shots down this 1 centimeter hole and measure the composition of the rock with depth. And here's just a view as we were getting closer and closer to the mountain. Well, I told you that we tried to drive through these valleys, and that actually was working very well for several kilometers. We could drive across the sand at the bottom of the valleys until we got to this valley that we called Hidden Valley. And now this valley had a lot of sand in it, very thick sand, probably 0.5 meter to 1 meter thick, and so much sand that it just formed this pattern of ripples across. And we were quite hesitant to drive across this particular valley, especially since there was, it filled the whole valley. And sometimes we can drive right around the edge of the sand, and keep one set of the wheels on more like a gravel surface. But here we really had no choice but to try to drive straight across. So we tested the rover in the desert in Southern California to make sure we knew how to drive it across these ripples. So we took a team of geologists out to the desert. We actually had to build these ripples because we couldn't find anything in the area that was the same as what we were looking at on Mars. And you can see that the rover that we use here is missing a lot of the hardware of the real rover, and that's because we have a real rover to simulate the Mars gravity on Earth. So this is a rover that, in all aspects of the wheels and suspension, is exactly like the one on Mars, but its pressure against the ground is the same as what would occur in Mars gravity. Well, we tried to drive across Hidden Valley, and after just a few meters, we almost got stuck. We came very close to getting stuck. In fact, for every meter that the wheels would turn, we were only making about 20 centimeters of progress. So we had about 80% slip. And that's when the rover sensed that it was slipping at 80% and automatically stopped driving. And then we were able to extract the rover the next day from the sand. But we decided we wouldn't risk it anymore, and we actually drove completely around this valley, and we had to find an entirely new path to get farther down the road. Well, I thought I'd show our methane result, partly because the Indian mission is measuring methane, and it's very exciting for us to see those results and compare them to what we're finding from Curiosity. So here is the measurements of methane that we've been making through the mission, all 2 years of the methane measurements, and you can see that we've found two things. One is we found a background level of methane, which is the long green bar, at about 1 part per billion, 0.7 part per billion. So it's very little methane, only 1 molecule of methane for every billion of air in the atmosphere. But then for just 60 Mars days, 60 sols around Sol 500, we saw a spike in that methane up to 10 times the background amount. And that was very surprising. Telescopic observers on Earth had seen fluctuations in methane, but it wasn't really, we weren't really confident that those telescopic measurements were accurate. And in fact, for the first year, all we were seeing was this very low background. But then, about 2 years into the mission, we saw this spike of about 10 times. And we have really no explanation of it at this point. There are different ways of forming methane. You can form methane from, on the bottom of this figure, you can form methane as rock interacts with water deep underground. This is a way that methane is formed on Earth. You can form methane from biology, microbes. We of course don't know of any on Mars, but it is a possibility. You can form methane through ultraviolet light, decomposing organic molecules on the surface. But all these would thought to be all these would thought to be something that would produce a very constant level of methane in the atmosphere. These would be very slow processes, and they would just gradually contribute methane to the atmosphere. So how do you get this very short spike of a tenfold increase? And we don't really know. One thing is you could store the underground methane in the form of ice, and that's what's shown in the bottom center of the diagram, methane clathrates. Clathrates are forms of water ice that can store methane in the crystal structure. And maybe you can form ice, trap the methane, and every once in a while that ice melts and releases the methane. We don't know why that would happen when we saw it, but it's one possibility. So finally, we have arrived at the bottom of Mount Sharp. Just in September, we finished our drive across the flat plains and are beginning now to climb up the mountain itself. And this is what the next few years of the mission will look like. We are now in the base unit. We're at the very first rocks associated with Mount Sharp. Over the next year, we'll reach the Hematite Ridge, which is a ridge of rocks that has a lot of iron oxide minerals, specifically hematite, that formed in quite a different environment. The iron oxide minerals would form in maybe an acidic environment, something probably not so friendly to life. Then just above that, remarkably, are where you see the clays. So then maybe the environment changed once again to something that had a lot of water and a lot of neutral pH water. And then finally above that are the sulfates, and we'll look forward to seeing what kind of environment is recorded in those rocks and whether it was a habitable environment. This is just a beautiful image that an amateur made. There's a lot of people who download our pictures and create these beautiful mosaics, sometimes much more beautiful than the ones that the team here creates themselves. So it's always fun to find these. And then finally, this is just a picture of everyone here who works on the rover. It takes about 100 people every day to operate the rover, and in the course of its development, it probably took about 10,000 people, engineers and scientists, to work on the mission. So it's fantastic. It's really fun. It's a lot of work every day. I can be pretty exhausted, but honestly, as you can imagine, it's the best job in the world. So thank you very much, and I'd love to take some of your questions.
He's asking what's the power source, like
the power source.
Yeah.
Yes. Let me try to go back here. Can you see my cursor?
Yes.
So in the back of the rover, maybe see you have a better picture. Well, in the back of the rover, it's a what's called a radioisotope thermoelectric generator. And so there is about 5 kilograms of plutonium dioxide, and that plutonium dioxide is radioactive, emits heat, and then it's encased in ceramic, and all throughout that ceramic are electrodes that convert the heat into electricity. And so that power source gives about 110 watts of power continuously, and then we store that power in a battery. And we run the rover during the daytime and pretty much drain the battery every day, and then we recharge the battery every night.
anything else?
I have a question. Sir, your presentation was really nice. I want to ask that is this a real-time monitoring of the machine, or how much time it takes to send a signal to the rover or get the signal from the rover?
Yeah, good question. So Mars is about between 7 minutes and 20 minutes away by the speed of light, and so it's just depending where Mars and Earth are in the orbit, which is just enough that it's impossible to command it in real time. Even when it's 7 minutes away, it would be too tedious to command it and wait 7 minutes for the reply. So we actually command the rover once per day. When the sun comes up on Mars, the rover finds Earth in the sky, and we send up 1 day's worth of commands. And about 6 hours later, the orbiters that are around Mars fly over the rover and get the data that the rover has acquired. And so the daytime, the time when the rover is actually doing what we command is about 6 hours. and just when the sun goes up to when midday on Mars. And then we have the rest of the Mars day, another 12 to 18 hours, to be awake here on Earth and come up with the next days of commands. And we actually, the funny thing is, Mars has a 24-and-a-half-hour day, and so the entire team here actually lived on Mars time for about 90 days. We all lived on a 24-and-a-half-hour day. We woke up about a half hour later every single day, and that was crazy. Our families didn't like it very much. It was the best way to run the rover. And after about 90 days, we stopped doing that. We still worked 7 days a week, but we would get out of sync with Mars. So we could command the rover every day for about 3 weeks, and then for the next 3 weeks, we would command the rover every other day. And that's how we've been doing it ever since.
So, what was some other suitable places for landing the Curiosity rover on Mars, and why we chose Gale Crater?
Sure. Yeah, I mean there were 60 different sites that we first looked at, and that's just sites that were appropriate for this particular mission to look at habitability. There are of course many other sites. If you want to look at the modern climate, you might go to the polar regions, where there's a record of the last few million years. But of course we were interested in sites that were about 3 to 4 billion years old, that were around when Mars was the most wet. And so we found 60 different sites, and we narrowed it down to the top 4. And briefly, these top 4 sites all address the habitability question in a different way. One site was completely made out of clays. It's the biggest clay deposit on the entire planet. So if you believed that clays were the key to understanding ancient water on Mars, this was your site. Another site had the best evidence for a lake on Mars. And so if you thought going to a lake was the best idea, then that was your favorite site. A third site was the Eberswald Delta that I showed very early in my talk, this beautiful river. And so some people thought that the delta was the most definitive evidence of there being a lake. And deltas also are places where on Earth you might drill for oil. And that's interesting because deltas, because they're the place where rivers drop their sediment into a muddy lake, they're actually where organics get concentrated. And that's why we find oil there today. So people thought if there was ever microbes in these rivers and streams, they might get concentrated in the deltas. And then finally, Gale Crater won out in the end, because really we don't know where the best place to look is. So with Gale, the idea was that it offered a little bit of everything. There was a river there. There was we thought there was a lake there as well, and we think that now actually. And so therefore, if there was a river and a lake, there probably was a delta in the middle somewhere. And then it had these different, it had the clays, but it also had the sulfates and the hematite. So maybe if clays weren't the best environment, maybe one of these other environments were. And that's the reason why we chose Gale. Can you repeat?
How
All
was
the places in the Mars, on the Mars are named. We have some names for most of the places.
Oh, I'm sorry. How about you repeat in the front row? I can hear you better.
So he wants to ask that how the places in Mars are named. Like, do we have assigned random names to them, or do we assign names on the basis of scientists who discover them, something like that?
Yeah, okay. So the big features like crater or valley, volcano, those are assigned through an international committee. So there's a committee called the International Astronomical Union. They got famous a few years ago when they decided that Pluto is no longer a planet. So it's the same body. It's that same committee that decides the names, how different planets are named. And usually it has to be, these features are named after historical figures that are no longer living. And sometimes there's themes like Venus. There's a lot of names of women. I think Uranus has a lot of Shakespearean names. I don't know how they come up with it. For Mars, anything that's big like that, the committee decides. So the Gale crater is named by the committee. But for small features, like when we just want to figure out what we're going to call the drill hole, what we're going to call a little pile of sand that we shoot the laser at, we're allowed to come up with our own names just to keep track of everything. And they don't have to be approved by anybody. So we actually name all of the features for Curiosity's mission off of important geological sites on Earth. So the Kimberley is a region of Australia where there's some fascinating geology. Yellowknife Bay is a place in Canada where some of the oldest rocks on Earth are found, and so on.
Sir?
Yeah.
Sir, why is reaching Mars so difficult? I mean, more than 2/3 of the missions have failed. So why is that?
Yeah, I think going anywhere in space is pretty difficult. First, there's launching from Earth, which has a lot of risk. Flying from Earth to Mars is probably the easiest part because you're just floating in space and nothing really can harm you. But then again, we have lost spacecraft even in that stage because they're exposed to very cold temperatures for 6, 7, 8 months. And then when they try to restart their systems and run fuel through the lines again, some things can be frozen. And actually, we lost the spacecraft Mars Observer for that reason. It was an Earth satellite that was then sent to Mars, and because it was designed to be around Earth mostly, it didn't survive those cold temperatures. And then, of course, the hardest part of all is landing on Mars. And that's because the transfer orbit to get from Earth to Mars and not fall into the sun, so to speak, means that you have to be going at about 6 kilometers per second. And so you blast off on a rocket from Earth, and then you use a booster to speed up and get out of Earth's gravity and out of the sun's gravity as much as it takes to get to Mars, and that puts you at about 6 kilometers a second. And then you hit a planet with an atmosphere. With the moon, you don't have this problem, but with Mars, it has a thick enough atmosphere where you have to have a heat shield, and so just the friction of entering an atmosphere means you can burn up. And then if you're not aimed precisely, you might not enter the atmosphere. You might skip out of the atmosphere, like throwing a rock on a pond. And then finally, if you don't slow down, you could still burn up, just in the fact that you're going from 6 kilometers a second down to the surface. And then, of course, you have the surface, so you have to slow down so you don't crash and destroy the spacecraft as you land. So you can imagine there's all these different steps that make it very difficult to get to Mars.
Sir, today do we have such technology with which we can land man to Mars and get him back to the Earth?
Yeah, no, I don't think we do yet. So NASA, of course, is trying to do that. And of course, it involves so much money that it becomes more of a political question than just a scientific one or engineering one. But we've talked about doing it for many decades, and there's still plans to do it. I hope to see it in my lifetime. But honestly, we're working our way towards it. So we've landed people on the moon, but and we've returned astronauts from space back to Earth, and they have heat shields and slowing down from very high speeds. So certain things we know how to do, but we've never sent a person so far away and had to deal with the communication issues with the same not being able to talk in real time. And then these missions would have to be about 6 months to get to Mars, then about 1.5 years on the surface before the planets are aligned again, where you can launch off of the surface and make it back to Earth for another 6 months. So this is about a 2+ year mission at the minimum. And that's more than anybody's ever spent in the space station. So even just the duration is very difficult. But we're taking steps there. With Curiosity, we've now landed something that's about 1 ton on the surface. And that's much heavier than anything that had ever landed on Mars before. And we think we have to get up to 10 tons and then up to 100 tons. We have to learn how to land that much mass on Mars to be able to land humans there with all of their life support equipment and the rocket that's going to take them home.
Sir, coming to life on Mars, initially, if we compare life on Earth to life on Mars, we kind of know what all ingredients we need for life, and still we are not yet able to figure out how life exactly started on Mars, because on Earth as such. Because some theory says that we have meteorites coming outside of the Earth's atmosphere, which began the process of life, the process of formation of amino acids as such. So, does the mission of Curiosity involves figuring out phenomena which started life on Mars, not just the ingredients which are needed for life, but the process entirely?
It's a tough question. I mean, I don't think we have not specifically designed Curiosity to do that kind of study. We're more equipped to do the habitability study, but we are looking for organics, and that's one clue. So our mass spectrometer also studies and looks for the presence of organic molecules, larger carbon-containing molecules, and that will give us some insight into whether, if we do find forms of life on Mars, or whether they use the same, like life on Mars uses the same kind of proteins, the same kind of RNA, DNA as life on Earth. If it was there on Mars, we could actually detect that with Curiosity. But really, we're mostly focusing on whether the environment was habitable. And the 2020 Mars mission, the one that's being developed now at JPL to land on Mars in 2020, will actually carry experiments to actually look for signs of life, whether it's ancient or modern. And I think that'll tell us a lot more about how life may have evolved on Mars.
So the question is, the graph which you showed of the hydrogen, of water and carbon dioxide varying with the temperature, is it from the past data or current data which Curiosity sends? As in, which place was the data from?
That was the very first drill hole. So it was a place, it was the drill hole called John Klein in Yellowknife Bay. This one. Yeah, so this is the place where we found the clay minerals, and now we've also found a very simple organic molecule called chlorobenzene in the same rock. I didn't talk about that, but in the same rock we've now found chlorobenzene. So we think we found organic molecules that have combined with chlorine in the soil, and remained for us to find 3 billion years later.
So what's the problem in using solar power?
The previous rovers used solar power, but they were designed to last about 90 days, and it was thought that when you could make solar panels on Mars in a very dusty atmosphere, but for 90 days they would still generate enough power reliably to keep the mission going. With Curiosity, from the start, we were designing a mission for 2 Earth years, and it was thought to be too risky to put solar panels on this rover to reliably generate power in the dusty atmosphere. Now, Spirit and Opportunity got lucky. It turned out those sites were very windy sites, and occasionally their solar panels would get cleaned off by the wind, which really wasn't expected. I don't think the same would have applied at Gale Crater. We're in the bottom of a very deep crater on Mars, and the top of our rover is getting quite dirty.
So I believe we can have one last question.
Yes, sir. Sir, what is the possibility that life actually began on Mars and was transferred to Earth by accident?
Yeah. We could all be Martians.
Yeah.
Yeah, it's a valid theory, and I'll give you 2 reasons. One is there has been a lot of work in the past 10 or 20 years on the fact that we see organics in asteroids, we see organics in meteors, and sometimes those can arrive on Earth pretty protected from degradation in space. So we think it is possible for molecules, maybe even living microbes, to survive a journey from one planet to the other. And then you couple that with the idea that Mars may have had all this water and fresh water in these exact sites where we drilled our drill holes at 3.5 billion years ago. And that's a time when Earth wasn't very friendly to life yet. Life on Earth evolved and really flourished later than that. So it's possible that Mars was friendlier to life earlier in the history of the solar system than Earth. And maybe that what you're saying is exactly what happened. But we'll have to see. One day maybe we'll be able to find early Mars life and look at its DNA and see if it has any similarities to ancient life on Earth.
Sir, I want to ask that, could you please throw a light on Mars 1 mission? Like, why we want to send humans to for one-way trip to Mars? Means, why we want to sacrifice them? Like, there is no water and there is nothing there, so why we want to send humans to Mars?
I don't want to go. No, it's a good question. I mean, this Mars One idea has really, I think of it more as a psychology experiment than a space exploration experiment. NASA is not ready to send humans. We're probably at least 10, 20 years away from sending humans. But this Mars One group, thinks it's possible and has asked for volunteers, and they got thousands and thousands of volunteers. So on the one hand, I think it's very interesting that people are genuinely excited, and people think that it's something that would make their life worthwhile to be the first people to go to Mars, even if it meant that they would not survive. And that just says something very interesting about humans, that we would.